What I'm going to do now is go ahead and start applying a first law analysis on some steady flow engineering devices. The first device that we're going to look at are nozzles and diffusers. So if you remember, what we may have covered earlier is the fact that a nozzle is a device that accelerates a fluid. So here's a nozzle, diagram of a nozzle, right? You have a cross-sectional area that is larger at the part where the fluid enters as compared to where the fluid exits. So the area at the exit is smaller than the area at the entrance. And the idea is that the fluid entering ends up accelerating to a greater velocity at the exit. And a diffuser does the opposite. The entering area is greater than the exiting area, resulting in the fluid decelerating to a lower velocity. And the idea of a first law analysis for a nozzle and a diffuser is that what's happening is that you're exchanging kinetic energy for the enthalpic energy of the fluid. How do I know that? I know that from a first law analysis. So let's go ahead and do this. This is a single stream first law analysis for a nozzle. So again, E in minus E out equals delta E system. Right? Steady flow, delta E system goes to 0. Therefore, I'm left with E in equals E out. So I'll go ahead and erase this and start right in E in equals E out. Therefore, as I go ahead and write in my first law, I get that all my energy in by heat plus work, this is a single stream, so plus the mass flow in, multiplied by that mass flow's enthalpy and kinetic energy, V squared over 2, and potential energy, equals the heat flow out plus the work out plus my single stream mass flow out multiplied by that mass stream's enthalpy and kinetic energy and potential energy. Now for this particular device, there's no heat flow in, there's no heat flow out, there's no work flow in, and there's no work flow out. So now I'm left with the mass energy in equals the mass energy out. And since the mass flow rates are equal, I can cross out the mass flow rates. And also, there's no change in potential energy in the mass flow rate in. So what I'm left with is my enthalpy in, we'll call 1 in, plus my kinetic energy in, equals my enthalpy out, plus my kinetic energy out. Right? And so what's happening is that the velocity going in is less than the velocity going out. So the enthalpy going in has to be greater than the enthalpy going out. This is the result of the first law analysis for a nozzle or a diffuser. What about for a turbine or a compressor? Well, again, these are steady flow devices. So I'm not going to go through the whole setup, but it would be energy in minus energy out equals change in energy of the system. Since this is a steady flow system, the change in energy of the system is 0. So I'm left with energy in equals energy out. So I get that energy in by heat plus energy in by work. And this is a single stream mass flow, right? Single stream mass flow in, single stream mass flow out. So I get the mass flow in, carrying that mass flow is potential. I'm sorry, enthalpy, kinetic, and potential energy equals the same thing out. Q out plus work out plus my mass flow out multiplied by the enthalpy, the kinetic energy, and the potential energy. Now, for my turbine, my compressor, if it is adiabatic, which means no heat transfer, there's no heat transfer. Right? Change of potential energy is pretty close to zero. Sometimes I can equate my change in kinetic energy to be at zero or close to zero. If it's the turbine, there's no work in, so it would be left with mass flow in multiplied by enthalpy and kinetic energy equals work out in case of the turbine, because there's no work into the turbine, there's only work out because the turbine is a work producing device, plus the mass flow out times the enthalpy and the kinetic energy. So I'm left with, for the turbine, if I bring this up towards the top of this slide here where I have some room, I get work out is equal to mass flow rate. I'll call this in is 1, out is 2. It would be H1 minus H2 plus V1 squared minus V2 squared over 2. In a lot of cases, the change in enthalpy is much greater than the change in kinetic energy of the fluid, so sometimes that can go to 0. Not all the time, but sometimes. And I'm left with work out is equal to mass flow rate times the change in enthalpy for the turbine. And it works out to be similar for the compressor, except you have the work in term which stays, and the work out term goes to 0. Right, so it all depends on what terms remain in the first law analysis. And again, as I mentioned before, for most turbines and compressors, there's no heat flow, and the change of potential energy of the fluid entering and leaving is 0. And often too, as I mentioned, the change in kinetic energy is at or close to 0, except for turbines and fans. So what you have is, again, this first law analysis that is for steady flow systems. This is only a first law for steady flow, right? This is a first law for a single mass stream first law analysis for a steady flow system. You have to understand what you're dealing with. This is not the result of a first law for every single device always, all the time. If I have a steady flow device, I get that my work in, heat in, and mass flow energy in is equal to my heat out plus work out plus mass energy out. This is for a single mass stream flow steady state engineering device. And again, according to this problem, if I'm looking at the compressor, if we assume it to be adiabatic, the Q terms go away, the compressor doesn't produce work, it consumes work. And if I assume that the change in kinetic and potential energy is 0 for the fluid, I end up with work in plus mass flow rate times the enthalpy in equals mass flow rate times the enthalpy out, or work in is equal to m dot delta H. Let's now look at what's called a throttling valve. What is a throttling valve? A throttling valve is a kind of flow restricting device that causes a significant pressure drop in the fluid. The pressure drop is often accompanied by a large drop in temperature. Right. So again, these are used a lot in refrigeration systems where you have the pressure on one side is much greater than the pressure on the other side, and that drop in pressure causes a drop in fluid temperature. Right? We call this an isentropic device because the enthalpy in is equal to the enthalpy out. How do I know that? Well, I'm going to go back and I'm going to rewrite my first law analysis for a single stream steady flow device. So heat in plus work in plus mass energy in equals heat out plus work out plus mass energy out. So I can assume that if the area of the valve is small enough, there's no heat flow. This device is definitely not consuming or producing work, and I can assume the change in kinetic and potential energy to be pretty negligible. And if my heat and mass terms cancel out for a single stream, my heat and work terms can't go to zero for a single stream, my mass flows also cancel out, basically equating that the enthalpy in is equal to the enthalpy out, calling it an isenthalpic device, meaning that the enthalpy is constant in and out. Again, all based on a first law analysis. What about for a mixing chamber? Right, last time you took a shower, you probably didn't realize you were using a mixing chamber. You have here a shower head. I have cold water coming into one part, hot water coming in. They mix together in order to get to the temperature of the water that you want for when you take a shower. So that's a mixing chamber, right? I have two mass flows in, one mass flow out. How does the first law analysis work on this one? Well, not any different. First off, I'm going to write my first law analysis for a steady flow system. All energy in by heat and work and mass equals all energy out by heat, by work, and by mass. All right, what do I do with this? Well, let's cross out the terms that don't belong. There's no heat, right? If this valve is insulated, there's no heat leaving or entering. And there's definitely no work interactions. If I assume my potential and kinetic energy changes the fluid to be zero, I get sum of the masses in, so I have mass 1 in times its enthalpy plus mass flow 2 in times its enthalpy equals the mass flow out times its enthalpy. That will be the result of a first law analysis for a mixing chamber. Let's go ahead and try first law analysis now for a heat exchanger. What is a heat exchanger? A heat exchanger is a device where two moving fluid streams exchange heat without mixing. Right, let's look at this case of a double shell or tube and shell heat exchanger. Right, I have one fluid entering and that fluid exiting, and another fluid entering and another fluid exiting. They are not mixing, but they're exchanging heat over a surface. Now the question is there any heat terms in the first law analysis? And the answer is, it depends on where you take the boundary. In this example of this heat exchanger, the boundary is taken around the whole heat exchanger. Remember, energy transfer is only recognized at the boundary of the system. So here I have mass crossing the boundary here, mass crossing the boundary there, mass crossing out of the boundary here, and mass crossing out of the boundary there. So I do not have any heat transfer. The heat transfer is occurring inside the system. I don't care what's going on inside the system. I'm only recognizing the energy crossing the boundary. Heat energy in for a steady flow device. Heat energy in by heat, mass, and work equals energy out by heat, mass, and work. There's no heat crossing the boundary. There's no work crossing the boundary. So the only energy interactions is occurring is by mass. But on this other scenario, where if I were to take my boundary across one of the fluids, in this case I have energy in by mass here, energy in by heat here, and energy out by mass there. So again, the result of my first law analysis all depends on where I take my boundary. Right, so if we go ahead and if we look at at an example, right? Let's do a quick example problem with this. So here is a heat exchanger. Let's see, I have fluid B entering here, fluid B exiting here, fluid A entering here, fluid A exiting there. So I'll call this, yeah, we'll just leave it like that. And this is insulated, right? How do I do my first law analysis? Let's go ahead. Let's write out, right, starting with En minus E out equals the change in energy of the system. Right, in this case, change in energy of the system is 0. So that means that energy in by heat, mass, and work equals energy out by heat, mass, and work. So if I were to go ahead and carry out this first law analysis, I would end up with energy in by heat plus work in plus the sum of all my mass flows in multiplied by each mass flows enthalpy, kinetic energy, and potential energy equals heat energy, heat flow out plus work out plus the sum of all my mass energy out multiplied by each mass flow rate's kinetic, potential, and energy and enthalpy. So again, if this is insulated, there's no heat transfer because I'm going to take my boundary around the whole heat exchanger. There's no work interactions. So what I have is energy in by mass in two places. So I have mass flow rate A times the enthalpy of mass flow A in plus the mass flow rate of B times the enthalpy of B in equals the energy out. So I have mass flow out at A and B as well. So I have mass flow rate times of mass flow rate A times the enthalpy of that mass flow exiting plus mass flow rate of B times the enthalpy of B out. So I can go ahead and take my mass flow rate terms. I'll put my A terms on one side of the equation. Mass flow rate of A times the enthalpy in minus out of A equals the mass flow rate of B times the enthalpy out minus in of B. So again, all this is just applying the same first law form for steady flow systems and basically just crossing out the terms that don't belong. And what you have left will be the first law in this form specific to the engineering device that you are analyzing.